Hello and welcome to the asynchronous learning recordings for Calculus 2 for Thanksgiving week 2024. As you go through these recordings, and it's encouraged you stop and think about these as well as attempt the problems prior to them being done and then check your work. If you have any questions about these, you are more than welcome to email me. So, without further ado, let's get started. So we're going to be talking about differential equations. So first of all, differential equations means any equation involving a function and its derivatives. When it comes to a variety of these, there are a whole bunch of these. Some of you may be taking differential equations this spring, so yes, we offer an entire course, and even that only scratches the surface of this. So for differential equations, an example of one is y double prime plus 7y prime plus 12y equals 0. Some details you'll learn later about. This is a second order homogeneous differential equation. Now, a solution to this, an example of a solution, would be y equals e to the negative 4x plus e to the negative 3x. That's not the only solution. However, you are welcome to check. But that solution, if you take the derivatives, then you plug them in, it will match with the differential equation. Now, and another example is if we have the differential equation y prime is equal to 3x squared plus 2x, one solution is x cubed plus x squared. To check it, just take the derivative. Derivative of x cubed plus x squared is 3x squared plus 2x. That's about as simple as it gets. However, we'll go through this gradually as some of you may not have seen these before. Checking whether equations are solutions to a differential equation merely involves taking the derivatives of whatever function we have and then plugging them in and making sure it's equal. So for the first example, we are told that the function y equals e to the 3x plus e to the 2x is a solution to the differential equation y double prime minus 5y prime plus 6y is equal to 0. If we take the first and second derivatives of the function e to the 3x plus e to the 2x, first derivative is 3 times e to the 3x plus 2 times e to the 2x. And the second derivative is 9 times e to the 3x plus 4 times e to the 2x. If we then plug these in, we get the equation 9 e to the 3x plus 4 e to the 2x minus 5 times parentheses 3e to the 3x plus 2e to the 2x end parentheses plus 6 times parentheses e to the 3x plus e to the 2x end parentheses. We can then combine like terms for which we get 9e to the 3x minus 15e to the 3x plus 6e to the 3x plus 4e to the 2x minus 10e to the 2x plus 6e to the 2x. Notice that 9 minus 15 plus 6 is 0, and 4 minus 10 plus 6 is 0. So all of that combined is equal to 0, and this function satisfies the differential equation. Please note this is not the only solution to the differential equation. More about what constitutes every solution on the to a differential equation will come later. Similarly, for the second problem, we have a slightly more term variety of this. So for the second problem, we are told that y equals e to the 4x plus 7x squared plus 8x is a solution to the differential equation y prime equals 4y minus 28x squared minus 18x plus 8. First of all, taking the derivative of the function gives us 4e to the 4x plus 14x plus 8. Now, if we calculate the other side of it and take 4 times the function minus 28x squared minus 18x plus 8, we get 4 times e to the 4x plus 7x squared plus 8x in parentheses minus 28x squared minus 18x plus 8. We can then distribute, and then following combining like terms, we get 4e to the 4x plus 14x plus 8, which is the exact same that we got for y prime, confirming that both sides of this equation are the same for the function e to the 4x plus 7x squared plus 8x. Again, this is not the only solution to that differential equation. However, we have successfully verified that this is a solution to it. One way of classifying differential equations is by talking about the order of a differential equation. This refers to the highest derivative present in the equation. For the order, we are only concerned about what derivative, meaning the first derivative, second derivative, third derivative on up. We are not concerned about what other parts are in. So if we look at the first differential equation, we have y double prime plus 7y prime plus 10y is equal to 5x to the third. On the left side of the equation, we have the first derivative as 7y prime, and the second derivative is y double prime. There are no other derivatives, so the highest order of derivative is 2, and therefore the order of the equation is second order. Next, we look at the differential equation 7y plus 4x to the ninth plus d5y over dt to the fifth plus 7 is equal to 17. In this case, the only derivative listed is a fifth derivative. The fact that we have x raised to the ninth has no effect on this, and neither does the fact that we have two variables that may be dependent or independent. The only thing that matters for calculating the order of this is that we have our highest derivative is a fifth derivative, and so this becomes fifth order. Next, look at the last equation. For the last equation, we have 5 times y triple prime plus 8y prime plus y raised to the fourth power is equal to sine squared of 4x. In this case, y raised to the fourth power and sine squared of 4x do not involve derivatives, so those do not affect the order. Instead, the order only would depend on what the highest derivative is. Y prime is a first derivative, and y triple prime is a third derivative. The highest of the two is the third derivative, and so this is third order. Next, I want to talk about solutions of differential equations again. What I would like you to do is pause the recording for about a minute or two and attempt these for yourself before listening and looking at what I found for these. As by exploring this for yourself, you may get insight that you otherwise would not get just by listening to me and looking at the work that I have done. So first of all, to find a solution to the differential equation y prime equals 3x squared minus 5, we are undoing a derivative. To undo a derivative, you can take an integral. So we can think of doing this as the integral of 3x squared minus 5. Or, on a similar note, we can think of this as finding a function whose derivative is 3x squared minus 5. Either way, we'll have x cubed, we'll have 5x, and we may have something at the end. So, for sake of just finding a function whose derivative is 3x squared minus 5, I came up with x cubed minus 5x plus 7. It works. It's not the only function whose derivative is that. However, if you take the derivative of x to the third minus 5x plus 7, you do get 3x squared minus 5, so it is a solution. When it comes to finding a different solution, I can do anything that has x to the third minus 5x plus a number. In this case, use c for a number, similar to what we did earlier with indefinite integrals. By the way, indefinite integrals, to solve an equation that is y prime equals indefinite integration is all that's needed. Now, this is a very simple example of a differential equation. So again, just simple integration does not solve many differential equations. However, knowing integration is an essential thing before you can even begin solving differential equations. Now, in the case of our set of solutions, meaning any solution that's out there, we have plus some number indicated by plus c. This isn't specific. We have now gotten a list of things that technically is infinite because we could add any number. So this isn't always helpful. Now let's consider a slightly different case. Let's say that not only do I want to solve this differential equation, y prime equals 3x squared minus 5, however, I also want my function to pass through the point 3, 10. If I do that, that forces me to choose -2 for c and gives the equation y equals x to the third minus 5x minus 2. You are welcome to check and you are encouraged to check. However, any other value of c will not go through the point 3, 10. You're also encouraged to check what the set of solutions x to the third minus 5x plus a number looks like, and that can be done using Desmos. As it turns out, the number at the end adjusts the height of the solution, and if we want a solution that specifically goes through 3, 10, we are forced to have c equals -2. The difference in terms of the first part of the last slide and the last part of the last slide illustrates two different types of solutions to differential equations. On the one hand, we have general solutions. A general solution is just a solution to a single differential equation. Well, actually, it can be a solution to multiple differential equations of multiple variables. However, that is beyond this course. More about that if you take Math 352 differential equations. And if you go beyond that, there are other courses that will go into that more thoroughly, such as a course on partial differential equations, which typically we do not offer at University of Jamestown. So a general solution is going to include at least one constant plus c. It can include more, and there are rules on that. If you would like to know more about that, you are more than welcome to discuss those with me and or email me. However, the example on the first and second part of the previous slide was an example of having a general solution, specifically the second part where we had a plus c, because the set of solutions to y prime equals 3x squared minus 5 are the set of functions x to the third minus 5x plus c. This is far from the only case, as if we look at the differential equation y double prime minus 5y prime plus 6y equals 0, we have the functions y equals c1 e to the 2x plus c2 e to the 3x. c1 and c2 are numbers that we can make whatever we want, and so long as those are real numbers, our solution will always fit with that differential equation. Now, on the other hand, if we set additional conditions, we can come up with a single solution. The example that we had at the end of the previous slide, where we specified that the point 3, 10 must be included in our function, is an example of a particular solution. And the 3, 10 is an example of a condition. For a first order differential equation with one independent variable, we will typically only need one condition. On the other hand, if you look below, if we take the differential equation y double prime minus 5y prime plus 6y equals 0, we need two conditions to get a particular solution. For this example, we have y of 0 is equal to 12 and y prime of 0 is equal to 31. Inserting those two conditions gives the general solution gives the particular solution, again, repeat, this is a particular solution, y equals 5e to the 2x plus 7e to the 3x. In case you were wondering, for a third order differential equation, you do need 3 initial conditions. To solve for particular solutions involves first finding a general solution and then inserting initial conditions to solve for the constants. Now, let's practice actually finding general and particular solutions, as well as checking whether a function is a particular solution. We will start out with finding a solution, specifically a particular solution, to the differential equation y prime is equal to 3x squared minus 10x that passes through the point 4 comma negative 7. To do this, we start by solving the general. We start by finding the general solution, which means just solving the differential equation y prime is equal to 3x squared minus 10x. In other words, we want to find an antiderivative of 3x squared minus 10x, which does mean just take the definite integral of it. Taking the definite integral of 3x squared minus 10x gives us the general solution y is equal to x to the third minus 5x squared plus a constant c. Now, that's a general solution. However, we want a particular solution. So think about, for the point 4 comma negative 7, what does the 4 tell us and what does the negative 7 tell us? If we think about this, 4 comma negative 7 is a point x is equal to 4, y is equal to negative 7. We can then substitute these into the equation, which results in us getting a new equation. Negative 7 is equal to 4 to the third minus 5 times 4 to the second plus c. We can then simplify the right side, which becomes negative 7 is equal to negative 16 plus c, and then add to get c is equal to 9. To be clear, we have not yet found a particular solution. We have the parts there to solve it. However, c equals 9 is not the answer. Emphasis added because I see this missed on quizzes and exams, and please don't let me see this missed on the final. Okay, picture me begging if you need to. Okay, the solution to this, the particular solution, involves plugging in 9 to our general solution, replacing c. So substituting into our general solution gives us the particular solution, y equals x to the third minus 5x squared plus 9. This is the final answer. Now, let's take a look at confirming that a function is a particular solution to a differential equation with a condition. So, let's consider the function y is equal to 3e to the 5x and determine whether this is a particular solution to the differential equation y double prime minus 25y equals 0 with the condition that y prime of 0 is equal to 15. So first of all, we need to check this general solution, because in order to get a particular solution from the previous example, we need to know we have a general solution to begin with. From earlier, to check to make sure the function is a general solution, we need to take derivatives and substitute into the original equation. Taking first and second derivatives of the function y equals 3e to the 5x, first derivative 15e to the 5x, second derivative 75e to the 5x. Again, chain rule, derivative of e to the 5x is itself times 5, so 3 times 5 is 15, and 15 times 5 is 75. If we substitute the second derivative in and the function itself in, to the differential equation y double prime minus 25y, we get 75 e to the 5x minus 25 times 3 e to the 5x. This results in 75 e to the 5x minus 75 e to the 5x, which is equal to 0. So this equation satisfies as being a possible solution to the original differential equation. We next need to check the condition y prime of 0 is equal to 15. To do this, all we need to do is plug 0 into y prime and ensure the result is 15. So y prime of 0 would be equal to 15 times e to the 5 times 0. Noting that e to the 0 is 1 and that 5 times 0 is 0, we have 15 times e to the 0, which is 15 times 1, and that's equal to 15. So that satisfies the condition. And given that our solution satisfies the general differential equation and our initial condition, we have a solution that's a particular solution for this situation. Thank you very much for watching. Again, feel free to email me with questions. Have a great week.